My name is Louis, and this is a joint work with my grad student when they work with me and my grad collaborator, Roberto from Lehigh. So this talk actually is inspired by storage system. And as you all know, most of the storage system, we are going to replicate it because that if there's failure, we can still ensure some nice properties. However, if there's multiple copies of data, there's a consistency issue that we need to deal with. And typical approach is to use consensus to make sure that they are having similar view or similar data, which the property that we want to focus on is called strong consistency. To be more precise, the notion is called linearizability. And if you don't know what that is, the high-level idea is that there are lots of different concurrent operations. And then when the clients or the user using the system, the observed result of the operation should appear in the same total ordering. So that as a developer, you don't need to think about that there are multiple machines. They behave as a single entity. And the advantage is that you don't need to resolve inconsistency issue or anomaly because of those conflict by hands. That's taken care of by this strongly consistent underlying storage system. So it's the complexity is much reduced. And in fact, lots of storage, real-world storage systems are doing the same thing, linearizable replicated storage, including systems from Google, Microsoft, Facebook, and lots of open source systems. And all the systems I list in the previous slide, they actually use the leader-based design or leader-based consensus to achieve this strong consistency. They use either Paxos or Raft or some variation. And you have a leader that I talk to the clients or the user. The basically leader say that, okay, this is the ordering that you should observe, you should behave, so that everyone can agree. However, this is not very scalable because the leader can easily be the bottleneck. Either the leader might be slow, or the communication between leader and application might be disrupted, or that sometimes the leader even fails, so that makes the problem difficult. And there are actually lots of literature trying to address this bottleneck of the leader, how to improve the performance of this kind of leader-based consensus protocol, or just consensus protocol in general. And roughly speaking, there are 4 categories of direction or solutions that I kind of use this consensus-based thing to improve the performance. The first one is that actually they are looking at slightly different models or assumptions. For example, there may be randomized consensus, there may be multi-leader solutions. And the second one is that say, okay, now that we have many advanced modern hardware that can provide more guarantee from the hardware layer, how can we utilize those more powerful primitives to improve the performance for consensus or the storage systems? And then the third one is that maybe they propose some engineer solutions that improve, say, batching or pipelining or different way of doing caching to improve the performance. And our paper, Pineapple, actually belong to the 4th direction. We propose new algorithm components that can be kind of compatible with existing consensus algorithms. And the motivation is that by adding new things, without changing the fundamental kind of design of the original, say, Paxos or Raft consensus components, that it's easier to be integrated with a real system. And actually, in our evaluation, we showed that it improves the performance of SCD. And the other insights that we kind of build our system on top of that is that We focus on the replicated storage that operate on key value pairs. And then they support, like most of those support 3 types of operations. The first is a read from a single key. The second is a write to a single key. The third one is a more general type of operations. We call it like one-shot transaction. So if you are familiar with this kind of APIs, you said, okay, well, single write, single key writes, actually that's a blind write. Excuse me, meaning that when you're doing a write operation, you don't care about what the existing value is, you just override it. But in fact, that's also common in lots of real-world systems. They just say, okay, whatever I do, I'm going to override the existing stuff. And then many of the systems also use this kind of notion of object storage. They provide different versions. So even for this blind write, you just add a newer version. So actually that is a very common solution in the practical system, practical design. And then some other usage of this kind of storage system or this particular API is that if you use this storage system to do some statistical analysis, then actually this blind writes can be very efficiently used if your operation have associated or communicative property. For example, histogram, hyperlog can be implemented using blind writes. So that's one of the motivation that we want to improve the performance for this type of operations. And then the other one is called one-shot transaction. So that the first one, a single key read and single key write, they only operate on a single key. But then in real world, we might want to touch multiple key at the same time. So one-shot transaction can do that. And then you also want to have a stronger synchronization power. For example, you might want to do read, modify, write, fetch and add, or compare and swap. And then in our design, you can do so through one-shot transaction. And if you are familiar with the database community, that's also called a store procedure. Basically, you already write some procedure stored inside the engine, and then you just call it. And it's one shot because that is not interactive. Okay, so in the API provided by Pineapple or our target applications, there's no interactive transaction. And then actually lots of key value storage, they only provide this kind of features. And here is one concrete example of what one-shot transaction is, which is a condition write. So you say that, okay, I'm going to write something to the key. Here for simplicity, I don't provide a value in this example. But then basically what that does, or one-shot transaction can realize this, is that first you check certain condition. Maybe say, okay, if the key already has some value, if the key is empty, then you can write it. Your write is successful. Otherwise, you don't want to override the existing key, so you will have failure. You have no write, okay? And you can think about that read, modify, write, compare, and swap. You can use the similar structure to implement that, okay? Cool. So now, this is the theme. The goal of this paper is that we focus on leader-based design, in particular on multi-Paxos, but we believe the mechanism we propose can be integrated with Raft as well. And then we want to provide 3 things: single key read, single key write, and one-shot transaction. Then how do we improve the performance? So this is a very simple picture for multi-Paxos. You have the leader there, and then client talk to the leader, and all the other are follower. They are just following what the leader does, but then they don't really interact with the clients. So to avoid the bottleneck, it's a simple idea. We make the follower do some work. We offload the single key read and write to the follower. So now they become the helper. And if you recall, we have one-shot transaction and we have read-write, so we separate the responsibility to different group of servers or different group of nodes. So now for read and write, the client will talk to other servers. So there are actually 2 components, right? The first part is that P part is a Paxos or multi-Paxos. They handle the one-shot transaction. And then there's A part, which is ABD, single key register. They handle the single key read and write. So that's basically the architecture or the high-level design of Pineapple. So the highlight is that we offload operations, and then as a result, we can provide lower latency and higher throughput. And then if you kind of follow this area, right? I mean, when we do replication, most cases we do 3-way or 5-way replication. So Pineapple actually can optimize for the n equal to 3, where n is the number of copies or number of servers you have. So in that case, the read is always 1 round trip time. So that's pretty nice. And then when you have a larger system, if there's no conflicting write, meaning that there's no write to the same key, then you can still achieve 1 RTT read. And then if your workload is read heavy, that's actually a very nice feature. And then the third highlight is that the execution is non-blocking. By execution is that for many of the consensus systems, they separate the agreement part and then execution part into 2 separate things. But for Pineapple, is that whenever you agree on something, whenever you communicate with a quorum or a leader, then you can execute your operations. However, for EPaxos or some other protocol, actually they don't have this property. So later on, when we visit the evaluation section, you will see the effect of this blocking versus non-blocking execution. All right, and then the key kind of components that we need to use in Pineapple is this Pineapple timestamp. It has 2 components. There's a tag one, there's a slot one. For the tag component, it's used by ABD, so you need to have a typical logical timestamp and a writer ID. And then for the slot, you have slot index plus some other stuff that you need to use for multi-Paxos. So on a high level, Pineapple use this timestamp to figure out which value is a newer version, and then how do you order operations. So Pineapple, as easy as ABC. The first one, you already saw it, is a Pineapple timestamp. And then the second one is that ABD part is use the tag component to do the single key reads and write. And then for the multi-Paxos part, it will use the second component, the start index, plus some other thing. If you know about Paxos, there's a ballot, that kind of metadata that you need to use to achieve consensus. And then here, actually, we need to have 1 more RTT for the Paxos component compared to the normal multi-Paxos. And the reason is that, remember, for the write, they might not contact the leader because they only contact the follower. So the leader need to learn the most recent value or most recent condition. So if you recall, right, this conditional write semantics I told you, leader might not know what the condition is. So it needs to have 1 extra RTT to figure out what's going on, and then it can compute the final result, okay? So you might think that, okay, 1 more RTT, that might not be good, but actually in our target workload, this is not a big issue. All right, so here is a picture explanation of what our protocol look like. For the write, it has 2 phases. The first one is I need to learn the most recent tag, and then the 4 is the largest one, so I need to add 1 to it. My new tag becomes 5A, and then I write back to it. And here, I don't touch the second part because that part is for consensus, is for Paxos. And for read is similar. I try to read the most recent tag, and then 4B is the most recent, is the largest one, so that's the value I get. And then if we assume that the client and server, they are co-located, actually most real deployment is like that, so we can skip the second phase because when I read it, I can update locally, so we already have a quorum of most recent value. Then that's how we achieve 1 RTT single key read. And then for one-shot transaction is slightly more complicated because we need to have this one extra phase. I need to get the value to check whether condition is met or not, if we are doing conditional right. And in this case, the most recent tag is 4B. And then I need to compute the new pineapple timestamp. And then here, as you can see, I'm increasing the second part, the slot index part, because that's through the Paxos component. Once I do that, I need to update the value to a quorum, then I'm done. Of course, there are some more technical details. For example, how do we do leader election? How do we handle concurrent operation? If there's multi-key operation, how do we do that? But I check the papers for detail. And for evaluation, in the paper, we check the throughput, latency, and then we also do that in the production system at CD, and we compare with like variation of a Paxos system, like multi-Paxos, the original one, and then MPL is a multi-Paxos with the leads, and Paxos quorum read, it's optimized for the read operations, and we also do compare with the EPaxos, and then actually there's one interesting paper also from NSDI. They combine EPaxos and ABD together, okay? And then actually I'm going to speed up because I want to have some time for discussion. So here is that in the local area network, and then as you can see, the pineapple, which is the orange one, the throughput kind of remains similar under different kind of config rate. Config rate meaning that whether the operation are accessing the same key or not. And then EPaxos, low conflict, it has good performance, but when you have high conflict, the performance drop. And then this is a throughput latency, and actually it's a tail latency figure. And here we have a higher throughput and lower latency, but because we optimize for write and reads. And then here, the orange one is us. In this case, we only have like one RTT read, and then this is wide area network. So as you can see, that's a very huge benefit for Pineapple. And then write, I'm going to skip this. And then for RM remodify write, or this one-shot transaction part, right? That's a kind of a slight more concern for Pineapple because we add one extra RTT to the system. So as you can see that yes, for most cases, the latency effect does show in this. But then if you recall, we said that we have non-blocking transactions. So here, actually, it's a straight line, but compared to EPaxos and Gryff, they need to wait for certain thing to happen, so they have this longer tail latency. All right, and then the final thing I'm going to show you is that we integrate Pineapple with ACD, and then we do a different kind of workload using YCSB workload generator. We do zip fan, and then I believe it's a high conflict one. So the throughput actually is not larger than Raft because Raft does some very high performance optimization for the read, which we didn't do. However, as you can see, under lower workload, actually our latency, both median latency and P90, 90% percentile latency, still better than Raft, even though we need to do one more RTT. So that's a nice thing. All right, so this is the final slide. The whole design is that we had two components. We separate read and write and one-shot operation. So if your workload is like that, you should try our design. That's all. Thank you.